Hey everyone, ever been deep into a calculus problem trying to solve a limit and you just get stuck? Well, today we're talking about an awesome shortcut that's going to feel like a superpower, L'Hopital's rule. Let's get right into it. So you know that feeling, right? You're cruising along, you've got a limit, you do the direct substitution, and bam, you hit a wall, 0 over 0. Or maybe infinity over infinity. It's what we call an indeterminate form, which is just a fancy way of saying, the answer isn't obvious yet. It means we got to dig a little deeper. And usually, digging deeper means a ton of algebraic gymnastics. I'm talking factoring, multiplying by the conjugate, pulling out every trig identity you've ever learned. It can get super messy, super fast. But what if I told you there's a much cleaner, much more powerful way to handle these? A real shortcut for when that direct substitution fails. All right, so let's properly introduce the bad guys here. These are the indeterminate forms, the roadblocks that tell us, nope, not that easy. And here they are, the 7 usual suspects. Now pay close attention to the top 2, 0 over 0 and infinity over infinity. These are the big ones. Why? Because they're the only ones L'Hopital's rule can handle right out of the box. As for the others, don't worry, they're still solvable. We just need a little algebraic trick to get them into the right shape first. So with all these roadblocks, how do we break through? Well, it's time to bring in the hero of this story, L'Hopital's rule. Okay, so here's the magic. The rule is actually pretty simple. It says that if you have one of those pesky indeterminate forms, you can just take the derivative of the top function and the derivative of the bottom function, and then try taking the limit of that new fraction. You're basically swapping out a hard problem for a much easier one that, incredibly, gives you the exact same answer. But why on earth does this work? Well, I love this explanation from Calc Workshop. Think of it like a race. You've got the numerator and the denominator, and they're both racing towards 0. Or maybe they're both racing towards infinity. L'Hopital's rule lets us check their speed. You know, their rate of change, which is the derivative. By comparing their derivatives, we're basically seeing which one is winning the race. And that's what ultimately determines the limit. Now, hold on. Before you start using this for every limit you see, there are some really important rules. You can't just go wild with it. First, it has to be a 0-0 or infinity-infinity form, no exceptions. Second, obviously the functions have to be differentiable. But here's the big one, the one everyone messes up at first. You take the derivative of the top and the derivative of the bottom separately. This is not, and I'll say it again, this is not the quotient rule. Please, please, please burn that into your brain. Okay, theory's great, but let's see this thing in action, right? Okay, check this one out. We plug in 0, and sure enough, we get 0 over 0. Perfect. So let's apply the rule. Derivative of the top is sine of x, derivative of the bottom is 2x. Now we check that limit. And, what do you know, it's still 0 over 0. But that's totally fine. It's not a mistake. It just means we go again. Apply the rule a second time. Derivative of sine x is cosine x, derivative of 2x is 2. Now can we plug in 0? Yes! Cosine of 0 is 1, so our answer is 1 over 2. See how cool that is? And hey, this thing isn't just for limits approaching 0. It's an absolute beast when you're going to infinity. Look at x squared over e to the x. That's a classic infinity over infinity situation. You apply the rule once, you get another infinity over infinity. You apply it a second time, and you end up with 2 over e to the x. As x goes to infinity, that denominator gets huge, so the whole thing goes to 0. It's a great way to prove something we intuitively know. Exponential functions just dominate polynomials in the long run. They just grow so much faster. All right, so we've mastered 0 over 0 and infinity over infinity. But what about those other 5 weirdos we saw? The products, the differences, the weird exponents? Well, that's where we get to do a little bit of clever algebra to whip them into shape. So here are the main plays in our playbook. The goal is always the same. Just use some algebra to make the problem look like 0 over 0 or infinity over infinity. If you have a product, you can use that old trip of dividing by the reciprocal to turn it into a fraction. If you have a difference, find a common denominator and combine them. And for those really nasty-looking powers, we have a secret weapon, logarithms. This log trick is a game changer, so let's walk through it. First, you just set the whole messy function equal to y. Then you take the natural log of both sides. The magic here is that this lets you use log properties to bring that pesky exponent down in front. Now you can solve the limit of this new expression, probably using L'Hopital's rule. But, and this is super important, you're not done. The number you get, let's say it's L, is the limit of ln of y, not y. So you have to do one last step, get y by itself. You exponentiate both sides, and your final actual answer is e to the power of L. Don't forget that last step. Okay, we've seen how powerful this rule is. It feels like a superpower. But like any superpower, you have to know when not to use it. Sometimes it's actually the wrong tool for the job, or worse, it can lead you completely astray. Just look at this beast. On the left, if you're clever and remember your special trig limits, you can rearrange this and solve it in basically one step. The answer is 1. Done. Now, look at the right. If you just blindly charge in with L'Hopital's rule, you're in for a world of pain. We're talking 3 applications, chain rules, product rules. The derivatives become an absolute nightmare. The lesson here? Sometimes the elegant, simple path is way better. Just because you have a hammer doesn't mean everything is a nail. So let's put this all together into a mental checklist. 3 big red flags. 1. Is the limit even indeterminate? If you can just plug in the number and get an answer like 0 over pi, well, that's just 0. You're done. Using the rule there will get you the wrong answer. 2. Does it lead you in circles? Sometimes applying the rule just gives you the same problem back again, an endless loop. That's a sign to try something else. And 3, the big one we just saw. Is there an easier way? Always look for a simple algebraic shortcut first. So where does that leave us? Is L'Hopital's rule a calculus superpower, or is it a tempting trap? Well, it's both. It is, without a doubt, an absolutely incredible tool that can crack open problems that would otherwise be impossible, but it's also so powerful that it's easy to overuse it and get stuck in the weeds. True mastery, true calculus wisdom, isn't just about knowing how to use the tools in your toolkit. It's about knowing which tool to pick for the job.